Hi, welcome back to Unify Physics. We are doing classical mechanics. So let's continue doing a few more problems. Especially we'll be dealing with two problems involving the constraint called rolling without slipping. Right? That the system should not slip during rolling. It's a constraint. All right, we'll see how to impose this constraint. That's the important thing, and then we'll obtain the Lagrangian and maybe the equations of motion for certain systems. All right, which involves this particular constraint. What do we mean? What do you mean by rolling? Rolling, it's a combination of two motions. You have got the linear motion, linear and rotation. Okay, if you have these motions together, then we say that it's rolling. All right. For example, there's a disk like that. The translational motion can be represented by the velocity v of the center of mass. All right, you've got a center of mass which moves with the velocity v. Here you have got the point of contact to the surface. Okay, and the rotational motion, let's say it also rotates with an angular velocity omega. All right, let's say the radius of this ring is capital R. All right, so what's happening here? You see that there's a point of contact here. All right, so this is rolling, fine. Okay, what do we mean by rolling without slipping? Without slipping. Okay. So when we said it's not slipping, it means that this point of contact, it cannot be dragged along this direction. Right? If it gets dragged here, then we said it has slipped. If it gets dragged here, we say it has slipped. All right. So the basic idea is that the instantaneous velocity of this point of contact has to be equal to 0. All right, the instantaneous velocity of this point of contact has to be equal to 0. Okay, so if you think about it, it's rather obvious. All right? Because if this point has a velocity, that means that it would move. The point of contact would move. All right, just gets dragged like that, and that would amount to what we call as slipping. Okay, so rolling without slipping means that the instantaneous velocity of this point, okay, the point of contact, instantaneous velocity is 0, which means that for this point, the translational velocity as well as the rotational velocity, they have to cancel each other. Right? So we know the rotational velocity is r omega. Rotational velocity is equal to r omega. Right? So the condition, the constraint, condition for not slipping while rolling. Okay, while rolling. It can be imposed like this. We can say that velocity of the center of mass, okay, since we are dealing with one dimension, we can just write it as VCM minus r omega has to be equal to 0. All right. What is r omega here? R omega is in this direction. Okay, that is r omega. So this is a rolling ring, and that's r omega. If V minus r omega, okay, VCM minus r omega is equal to 0, we say that it rolls without slipping. If this is not equal to 0, that means that it gets dragged a little bit. Okay, so that's the condition. That's the condition. You see that it's the condition on velocities. It's a condition on velocities. Okay, but for problems that we will solve, or most of the problems, or many problems, that we'll see that this condition on velocity can be integrated and made into a condition on the coordinates. Okay, that's what we will do. So let's start by solving one problem of this manner. Write the Lagrangian for a disk of mass m and radius b rolling down an inclined plane without slipping. All right. So the diagram is given here. This already suggests what generalized coordinates we can take. We can take x from here, at the distance from here. That's one of the coordinates, and you also have theta. Okay. So generalized coordinates. The generalized coordinates. Okay, let's take them as x and theta. All right, x will tell you at what position it is here. All right, and theta will tell you about the rotation, the rotational motion. Okay, x and theta. All right. So before imposing the constraint, let's see if there's. So let's write it generally. All right. Let's assume there may be slipping or something. Let's write the kinetic energy and the potential energy without assuming that there is no slipping. All right. So first we can write it like this, and then we'll impose the constraint. Okay. So the kinetic energy, it can easily be written as half m. Okay, because it's a disk of mass m. All right. Half m x dot square plus. Okay. You have to remember that this is a disk. This is a disk, and so there will also be half I omega square. right? It has a moment of inertia. I is the moment of inertia of the disk, all right? And this is of radius b, so we can write I is equal to half mb square, right? That's the moment of inertia for a disk. This is what we have to use. So this is actually theta dot square, right? So there are two contributions to the kinetic energy. One is due to the motion of the center of mass, that's half mx dot square. The other one is due to rotation, right? This is the contribution due to rotation. This is moment of inertia, okay? We know that the kinetic energy due to rotational motion can be written as half I omega square, all right? So you need to know the moment of inertia, how to calculate the moment of inertia for this disk. So you can look it up, and it's equal to half mb square. So the kinetic energy is equal to half mx dot square plus half m, right, half multiplied by half mb square theta dot square, right? So that's the total kinetic energy. So I'll just write here, we have got T equal to half mx dot square plus half m b square theta dot square. Okay, is that correct? Yes, half mb square theta dot square. That's the kinetic energy. What about the potential energy? What about the potential energy? The potential energy, you see that it depends on the height here, right? How you can take this as the height, all right? So you can take this as the reference point, this bottom line as the reference point. So this height is actually, this length is L minus x, right? This length is L minus x, so this has to be L minus x sine alpha, all right? The angle of inclination is given here, so it's L minus x sine alpha. So V is equal to mg L minus x sine alpha, right? So the Lagrangian would be half mx dot square plus 1 by 4 m, we can write as b theta dot square, okay, minus mg L minus x sine alpha. That's the Lagrangian, okay, all right. So this is the Lagrangian if we don't impose the constraint of not slipping, all right. This is the Lagrangian just for rolling motion. If we just assume that the disk is rolling along inclined plane, and this would be the Lagrangian, all right. But now you are asked to impose an extra condition that there is no slipping. There is no slipping. There is no slipping. That means the condition for that we have discussed already is that the velocity of the center of mass is equal to the rotational motion, or x dot minus, all right. What is r omega here? In the place of r you have got b, that's the radius, and omega is theta dot, okay. X dot minus b theta dot is equal to 0, okay. This is the condition for not slipping, okay. So you see from here that x dot is equal to b theta dot. So the Lagrangian now becomes L equal to half m. We can choose x dot, all right. We can eliminate theta dot. We can choose. So you see that the constraint says that there is only one generalized coordinate. You don't need both theta and x. There is an equation connecting them, all right. The equation connecting them is known as the condition for no slipping, okay. So L equal to half mx dot square plus 1 by 4 m b theta dot is equal to x dot, okay. X dot square minus mg L minus x sine alpha, okay, all right. Now we can write this is equal to 3 by 4 mx dot square minus mg L minus x sine alpha, okay. That's the Lagrangian. Okay. Now you can as well choose theta dot as the generalized coordinate, or theta as the generalized coordinates. Okay, you can also choose theta as the generalized coordinate, okay. All right. So the thing is that there is only one generalized coordinate. So if you choose, you could also choose depending on your purpose, all right. What purpose you want to do in your problem, right? What's the purpose in your solving the problem? You can also write it in terms of theta, okay. Let's write it here. If theta is the generalized coordinate, theta is the generalized coordinate, okay, then what happens? As we said, we can use x dot is equal to b theta dot, x dot equal to b theta dot. So you'll substitute this x dot in terms of b theta dot. Okay, so you see that L is equal to we could either do that here, right? We can do that here. That will be 3 by 4 mx dot here. That 3 by 4 m. What was x dot? What is x dot? Sorry, x dot is equal to b theta dot. So 3 by 4 m b theta dot square. B theta dot square. Okay. You have to be a bit careful here. Minus mg L minus x. There's an L minus x over there. There's an L minus x and sine alpha. Okay, that's the Lagrangian. What's x? Alright, so remember that we have the condition on x dot. We have the condition x dot is equal to b theta dot. Alright, so this condition can be integrated. Even though it's a condition on velocities, you can integrate it and find the relation between the coordinates. Alright, because this is dx by dt and this is d theta by dt, you just integrate it and you can see that x equal to b theta is the relation. X is equal to b theta. Okay, so here we have to take the initial condition that when x equal to 0, theta equal to 0, right? We can choose the initial condition as theta is equal to 0 when x equal to 0. So here it becomes b theta. Alright, so this is the Lagrangian in terms of theta. If theta is the generalized coordinates, if you want to choose theta as the generalized coordinates, you should write the Lagrangian in this form. Okay, I hope that's clear. Alright, the important point here is that this is a condition on velocities, but we can actually integrate it to find a condition or find a relation between the coordinates. Okay, right? We can step up and do a slightly more involved problems, not particularly difficult. This is another problem involving rolling without slipping. Okay? The figure shows a solid cylinder with center G. Okay, this is center of mass. Alright, we can say that center of mass is G and radius A rolling on the rough inside surface of a fixed cylinder with center O and radius B greater than A. Alright, so you have got one fixed cylinder. This radius is B. Okay, this radius is B. And then there's a smaller cylinder here with radius A. Alright, there's a smaller cylinder here with radius A. Find the Lagrange equation of motion and deduce the period of small oscillations about the equilibrium position. Okay, so as we said before, we need, okay, so we just need to find the equation of motion. We need to write down the Lagrangian, find the equations of motion, and then find the period of small oscillations. Okay, so let's see how to do this. All right, so for this condition, we said that we need the center of mass. Okay, so this is we are talking about a cylinder here which is rolling like this. All right, there's a cylinder which is actually rolling. Okay, so it has a center of mass. What's the velocity of the center of mass? This can be found with respect to this because it's confined to the inner part of the bigger cylinder, inner surface of the bigger cylinder. Okay, so we see that this length, this is b minus a. Okay, and the velocity, the angular velocity is theta dot. So this is b minus a theta dot. That's the velocity. All right, that's just v is equal to r omega thing. So v with the velocity of the center of mass is b minus a multiplied by theta dot. Okay, all right. So that's b minus a multiplied by theta dot. We have got the velocity of the center of mass. Okay, what about the angular velocity or the rotation, velocity of rotation? Okay, due to rotation you have a, so we have got the velocity of the center of mass. Now this is actually rolling, so it has also rotational motion. So the rotational velocity, so to speak, the rotational velocity, let's call it as rotational velocity for the time being. Okay, you can say omega, that's equal to, okay, we take this angle as phi. Okay, we take this angle as phi and the radius is a, so that is a phi dot. Okay, so the rotational, the angular velocity is phi dot, so corresponding linear velocity is a phi dot. Okay, now immediately you know the condition, the constraint that it is rolling without slipping. All right, the constraint that it rolls without slipping is b minus a multiplied by theta dot is equal to a phi dot. Okay, just as we said, VCM is equal to r omega. All right, so this is the velocity of the center of mass and this is the velocity due to rotation of your inner cylinder. Okay, this is the constraint. Okay, I hope that is clear. Constraint. Okay, now we can write down the Lagrangian. So first the kinetic energy. Okay. Kinetic energy, again it has two two contributions. One is due to the motion of the center of mass. So are we given the mass of the center of mass here? Sorry, are we given the mass of the cylinder here? Not, yeah, it has a center G and radius A rolling. Okay, so let's write the mass as m. Okay, let's write the mass as m. So the kinetic energy is T is equal to half m, okay, and VCm square, all right, VCm square, all right, and what's VCm? It is B minus A multiplied by theta dot square. That's just one contribution, all right. You also have the contribution from the rotation, which you can write as half I omega square, and omega is phi dot, okay, half I phi dot square. It's a solid cylinder, okay. All right, so that's that, and yes, okay, so it's the kinetic energy, but we need the moment of inertia, right? So moment of inertia, okay. So if you look up the solid cylinder, okay, you'll see that there are three components, of course, but the component that matters here, the component associated to which there's a velocity, is actually Iz. Okay, we can call it a Iz, and that's equal to half m a square. Okay, that's I is equal to the relevant component of the moment of inertia can be written as half m a square. Okay, all right. So the kinetic energy now can be written as T is equal to half m b minus a theta dot square plus half I phi dot square, and what's I? That is half m a square phi dot square. Okay, now we just simplify this, so this becomes half m b minus a square theta dot square, okay, plus 1 by 4 m a square, or we can write as a phi dot square. Okay, now we can impose the constraint that it's actually rolling without slipping. The condition is that we already wrote it down here, b minus a theta dot is equal to a phi dot. So the a phi dot here we can write as b minus a theta dot, or this b minus a theta dot here we can write as a phi dot. Okay, so let us choose theta. There's only one generalized coordinates, and let's choose it as theta. You can choose also phi depending on your purpose, but theta as the generalized coordinate. Okay, so what do you have? The kinetic energy becomes, this is 1 by 2 and this is 1 by 4, that's 3 by 4 b minus a square theta dot square. Okay, you just substituted a phi dot is equal to b minus a theta dot. Okay, that's the kinetic energy. That is the kinetic energy. What about the potential energy? V is equal to, so if you look here, we can take this point as the reference point, as the zero of the potential energy. Okay, so the height, okay, the height here, it is equal to, this is b minus a, so the height here is b minus a cos theta. That's the height. Okay, so we have got v is equal to minus mg, because we have taken the point O as the reference point, so it's minus mg b minus a cos theta. Okay, b minus a cos theta. So our Lagrangian now is 3 by 4. Okay, Lagrangian is 3 by 4 m. Okay, we'll write as b minus a whole square theta dot square. Okay, plus, because it's t minus v. Okay, cos theta. Right, let's look at the equation of motion. Equation of motion for theta, because we have only one generalized coordinate. So equation of motion for theta becomes, if you look at it, this becomes d by dt of dou L by dou theta dot, dou L by dou theta dot. That's simply 3 by 4 m b minus a square theta dot. So this becomes 2 here. Okay, because theta dot square, derivative of that is 2 theta, so it's 3 by 2 m b minus a square theta dot is equal to minus mg, because dou L by dou theta, is c cos theta, so derivative of cos theta is minus sin theta, that's why. So minus mg b minus a sin theta. Okay, all right, so all these things are constants, so we see that 3 by 2 m b minus a whole square theta double dot is equal to minus mg b minus a sin theta. That's our equation of motion. Okay, we can simplify it, of course. This m and m will go, this square can be cancelled once. Okay, so you see that we can write as theta double dot is equal to minus 2 by 3, we have got a g there. Okay, so just rearrange. Okay, 2b minus a, 2g by 3b minus a. Okay, theta double dot is equal to minus 2g, is that correct? Yes, minus 2g by 3b minus a sin theta. Okay, or we'll write here, you get theta double dot plus 2g by 3b minus a sin theta is equal to 0. That's your equation of motion. Okay, that is your equation of motion. Now we are asked to find the period of oscillations for small oscillations. Okay, period of oscillations for small oscillations. So for small oscillations, we can take the condition sin theta is almost equal to theta, or sin theta is equal to theta. Okay, so when you take sin theta is equal to theta, you get theta double dot plus 2g by 3b minus a theta is equal to 0. Right? Now if you look at the linear harmonic oscillator, for example, simple pendulum for small oscillators, you will see that it has exactly the same form, except that it is of the form theta double dot plus omega square theta is equal to 0. Okay, plus omega square theta is equal to 0. Okay, all right. So that means that, just a second. Right, so that means that omega square is equal to 2g divided by 3b minus a. Okay, and right, so omega is equal to square root of 2g divided by 3b minus a. Okay, and what's the period? Period t is equal to, write it here, t is equal to 2 pi divided by omega. So that becomes 2 pi square root of, take it from here, so 3 by, that becomes 3b minus a divided by 2g. Is that correct? 3b minus a divided by 2g. That's the period of oscillations. Okay, that is the period of oscillations. I hope that's clear. So we have done two problems involving the constraint called there's a rolling without slipping. Okay, I hope now you can you can actually impose this condition in any problem if such problems are asked in the examination. Okay, so let's just do one more problem and then conclude. The third problem we are going to do today is called the compound pendulum. Okay, a rigid body capable of oscillating in a vertical plane about a fixed horizontal axis is called the compound pendulum. All right, so there's a rigid body which can actually oscillate about a point on itself. All right, there's a point here, it can actually oscillate. Okay, so G is the center of mass here, this is the center of mass. Okay, so we are looking at the motion of the center of mass. Now we are asked to set up its Lagrangian, obtain its equation of motion, and again find the period of the pendulum. Okay, so let's do it for small oscillations again. Okay, period of small oscillations for the pendulum. So immediately we see that we can choose theta as the generalized coordinate. Okay, right, and the potential energy becomes, we can take this as the 0 of we can take this as the 0, that's the easiest point. We can take this as the reference point of the potential energy. So V is equal to minus mgl cos theta. This is the easiest choice of the reference point. Okay, and what about the kinetic energy? Kinetic energy is equal to half I omega square. Okay, it's half I omega square. So for the particular rigid body that you might be working on, this expression for what do you say, the moment of inertia will be different. If it's a disk, it will have a different moment of inertia. If it's a cylinder, and it will have different components. Okay, so you have to do that. All right, for now let's we are not given the exact kind of rigid body we are talking about. Okay, so we can just write it as half I omega square, and the Lagrangian is simply half I, what's omega, that's theta dot. Okay, half I theta dot square plus mgl cos theta. That was not very difficult, that's quite easy. Okay, that's quite easy. So we have got the Lagrangian L is equal to half I theta dot square plus mgl cos theta. Okay, and the equation of motion is just do what we have been doing, so that becomes I theta double dot plus mgl sin theta is equal to 0, and for small oscillations again you can take sin theta is equal to theta and you get I theta double dot. This is not a very difficult problem, okay, it's an easy one. You just need to know how to start the problem, all right. So I theta double dot plus mgl theta is equal to 0, or we can say theta double dot plus mgl by I theta is equal to 0, all right. Now just as before, you do the comparison and we will see that t is equal to 2 pi, let's write it like this, square root of I divided by mgl, okay. That is the period of oscillation, okay. That's known as the compound pendulum, right. So in today's class what we have discussed is mainly the problem involving rolling without slipping. We have seen that the constraint corresponding to rolling without slipping is a condition on velocities, okay, which is velocity of the center of mass is equal to r omega, okay, r omega. That was the condition, right. So we also saw that it can be integrated in the cases that we discussed. It can actually be integrated and written as a condition of the coordinates, all right. So that also is possible. You just need to fix the initial conditions, all right. Now once we know that, we can solve problems involving rolling without slipping. Okay. Now I hope you have understood, you have followed the class. Thank you. We'll meet in the next session.